one thing to note about lookasides lists is that when you boot a system, it's not used because they want to reduce the memory footprint or something. So you'll see that if you look at the NTX pool flags, right after you booted a Windows system, you'll see that the 100 hex is set. That is the cold separation flag, hot and cold separation flag. So I think the timeout is 2 minutes. So if you want to do some look-aside tricks, wait 2 minutes after having booted a system, otherwise you'll end up using the free lists. So again, this is how the session part of the look-aside lists are put into the specter of whatever. So yeah, you have the empty mm session space that defines the mm session space structure that holds all the lists. You also have some dedicated look-aside lists. I won't talk too much about those, but obviously the kernel does a lot of allocations of the same size. So it requests I/O request packets, uses those MDLs, object-created information structures, a lot of different things it does all the time. So it has like an optimized way of it has its own look-aside list for that to service those requests rapidly. And these are defined in the KPRCB block, like I mentioned before, or you saw. So in the event that an allocation cannot be serviced by a look-aside list and is larger than a free list holds, it will resort to the pool page allocator. And this is for allocations greater than 4,080 bytes. And it's handled by a function called xallocate big pool that internally calls, the pool page allocator itself. So xallocate big pool is actually just kind of a wrapper around the pool page allocator to, divide the remaining chunks that weren't used to put those on free lists, stuff like that. And we also have look-aside lists for this as well. So there's like a look-aside list for pages, so one page size or 2 page size, whatever. So yeah, it gets kind of confusing in the end. But we don't really need to care too much about this. We're primarily going to focus on the look-aside and the free lists. So if a look-aside cannot be used, it will try to use a bitmap to find the pages it needs. And this is, again, it's an optimization. And every major pool type has like a bitmap associated with it. So we'll scan the bitmap. Let's say you want eight pages, 8,000 bytes hex. So it'll just scan the bitmap for the contiguous number of pages and return the address. It's really simple. So to summarize, so when you were operating on all these lists, we actually just use one function that is xallocate big pool with tag. So this function will first look at the look-aside lists, the list-as lists, and then the pool page allocator, which I've now talked a bit about. And Windows 7 in particular uses safe unlinking when you pull a chunk from a free list. This is really important because this was actually, this is what killed all the attacks before. Safe pool unlinking or just safe unlinking is basically just validating. So when you pull the middle chunk out, you want to make sure that the previous chunk's f-link point back to whatever that b-link in the middle chunk pointed to. And likewise on the other side, you want to make sure that that right chunk's b-link points back to the address that it was indicated by the chunk that you unlinked. So I'm sorry if that didn't make sense, but that's safe unlinking, and it works when it's implemented correctly. Unfortunately, they didn't do that, so, well, they almost got it right. So this is the allocation algorithm. I'm going to go quickly through it. It's not that complicated. So the first thing it checks is that if the size is larger than FF0 hex, then it will call the full page allocator or the wrapper. If it's not, it will look at the type, and it will try to use the look-aside list for the associated types. So first for the page pool, non-page pool, or sorry, page pool in the session. If it can't, it will go to the list heads list or the free lists. Yeah, so this is like, yeah. So if it cannot be serviced by a look-aside, it will look at the free lists, and it will iterate through each block size. So it will try to find the block size that it requested. If that is not present on that particular list, if there's no unavailable chunks, it will just go on to the next one, until it finds one, and then return that and split it. If it's larger than it needs, it will split it. So before we go into splitting, this is a diagram showing how I don't know, simple or complex you can make things. It's kind of simple though. It's not that complex. If you want this diagram, let me know. Otherwise, I'll put it up somewhere. So when you split a chunk, it has some optimization made to it. So for instance, if the chunk is page aligned, it will allocate the fragment that it will use will be in front. If it's not, it will use the lower part of the chunk, and that is just to make the fragmentation as small as possible. So this is what that looks like. Yeah, you start with a free pool page. The first allocation is on the top, then subsequent allocations will be made from the bottom up. This is actually really important if you think about kernel pool manipulation, making holes, stuff like that, because you're not doing top to bottom, you're doing top and then bottom up. So it's kind of important. The free algorithm it works pretty much as expected. It basically looks at the pool header and frees it to the appropriate list, based on the block size and the pool type and the pool index. So yeah, and it will try to merge it with the free chunks around it to reduce fragmentation. And Windows 7 uses safe unlinking again, because when you merge a chunk, the chunks around it, they're free, but they're on the list, so it will pull those out of the list in order to merge them again. So in pulling those out of the list, it will safely unlink those. That was one of the previous attacks. I'll talk a little bit about those in the next section. Okay, so I'm almost done with the internals. This is a couple of more slides. So the free algorithm, like I said, if the free is page aligned, means that it's a full page. It will free call the full page the allocator or free or whatever. It has some basic checks. So for instance, if you free a chunk, it will see if the block size of that chunk corresponds to the previous size of the next chunk. So that's kind of like a weak buffer overflow detection of some sort, corruption. It's easy to get past. Just, if you overflow from a chunk, you basically know the size of that chunk. So it's not really useful. It's more for a corruption detection kind of thing, for in case developers do stupid stuff. It will try at first to free it to a look-aside list. If the list is full, it will go on to use the free lists. And this is, here you really have two options. There's something called delayed freeze, which is the performance optimization usually used in most systems. If that is the case, I believe an explanation is coming up on the next slide, but if that is the case, it will use its own function and put it on the referred free list. If it doesn't use delayed freeze, it will free it immediately and do the merging and unlinking and So to summarize, this is the algorithm pretty much. Again, not terribly complex. So seems kind of manageable. Yeah, so this is just trying to illustrate the merging process. So in this case, the busy chunk in the middle is going to be freed, so it will unlink the right chunk, merge with that, unlink the previous chunk, merge, and then mark everything as free and return that to the lists. This is the basic functionality of the free algorithm. So I mentioned delay pool freeze. And this is really a performance optimization made to avoid, locking the pool every time, because that, takes a lot of time to be in if you lock it every time. So, whenever you have more or around 512 megabytes of RAM in your machine, you'll be using this optimization. So pretty much everyone uses it without knowing, maybe. And what this does is that it appends the chunk on the pending free lists, and if there's 32 entries on that list, it will process all the chunks in one go. So it will actually just lock the pool descriptor and then process all the entries and then unlock the pool descriptor instead of locking free unlock, locking free unlock. It's a lot more efficient. And one of the attacks is also on this particular list, because they're chained together on a single linked list while not being used. So if you manage to overflow into one of the entries on this list, you can basically, pick which chunk to free next. So we'll see how that works later. This is the algorithm for the deferred free pool. It's pretty much the same as the previous free algorithm, except that it iterates through all these chunks on that list and merges if it's a full page, puts on the full page, calls the free pool pages function. Yeah. So this is the last slide of internals. I don't think anybody. Oh, there's someone over the split. Damn. Okay. So this slide is not that important to understand now, but it's really important to understand if you're gonna do this for some, I don't know, if you have little to do at the weekend or whatever. So it's about when you fragment a chunk, or when you split a chunk. There's a bit of deviations in what part of the list the chunk is put. So sometimes it's put in front, other times it's put in the back of the list. And the thumb rule to this is that whenever you free a chunk, it's always put in the front. And that is really to reuse the CPU cache as much as possible. When it's split, if a page is split, or if it requests a block size larger than what it requested, so it had to split it, it's always put in the back. I don't know why they don't put it in the front. Doesn't really make sense, but that's how they do it, I guess.